All right, back to the idea of universal constants. The first universal constant we talked about was c, the speed of light. It is 3.0 times 10 to the 8th meters per second. Okay. Now the thing you need to understand about the speed of light is that it is the cosmic speed limit. It is impossible for anything to move faster than that in this universe. Later on, if we have time, I'll show you why. But for our discussion today, just accept, I'm going to ask you to suspend disbelief, and that's a time-honored academic exercise, to just accept for the purposes of this discussion that is the cosmic speed limit. So if we have a cosmic speed limit, then that actually presents us with some problems. And I'm going to set up a problem here to illustrate this. I'm going to create an imaginary clock. And I'll tell you right off the bat, this is going to be kind of a ridiculous imaginary clock, but that's okay. It's going to start with two perfect mirrors facing each other. Sealed into a tube. And we're going to pump out every last atom and molecule out of this tube so that it is an absolutely perfect vacuum. The only thing that we're going to leave inside this tube is one little photon. And he's just going to bounce back and forth between these two mirrors. Oh, and this clock, this contraption here, is going to be 3.0 times 10 to the 8th meters in length. That's 186,000 miles. So that's my clock. Tick, tock, tick, tock. It's going to take that little photon 1 second to go from one end to the other, traveling at the speed of light. But being the nerd that I am, I can't resist. I'm going to install a couple of rocket engines on it. And I'm going to light them off. And off we go. And we're going to get up to 1.5 times 10 to the 8th meters per second. Now, as ridiculous as this contraption may be, well, it is, it's still something that is, in a wacky sort of way, possible. So let's look at what happens after 1 second of travel. After 1 second of travel, this contraption will have traveled 1.5 times 10 to the 8th meters in that direction. Meanwhile, the little photon will have traveled 3.0 times 10 to the 8th meters in that direction. But for us, watching this contraption go by, what do we see? We see the photon move in that direction. And if you do a little bit of geometry here, if you use Pythagorean's theorem, we see that this photon is actually covered, from our perspective, 3.35 times 10 to the 8th meters. Whoops. That's a no-no. So, what do? Something's got to give here. If we're going to insist that that photon covers 3.35 times 10 to the 8th meters, and if we're going to insist that that's as fast as he can go, then we're going to have to give him more time to cover that distance. If, on the other hand, we say, no, 1 second, that's all you get, and this is all the distance you get, then what's going to happen here? Well, this is going to have to be less than 3.0 times 10 to the 8th meters. So one of two things is going to have to happen here. Either the time is going to have to expand, or the length is going to have to contract. And it turns out that is exactly what happens. When we get into this realm of speed, or for that matter, this realm of speed, half the speed of light, weird stuff happens because it has to. There has to be a safety valve here somewhere. How do we account for that safety valve? Well, we use something called the Lorentz factor. The Lorentz factor is the square root of 1 minus v squared over c squared. Velocity over the speed of light. And the velocity is expressed as a fraction of the speed of light. It's expressed as a fraction. So, let's try an example here. The best way to get into this one is to try an example. This, by the way, is also referred to as gamma. It's kind of a funky looking Y, Greek letter gamma. So, let's try this one. Let's say that we have a spaceship flying past NASA ground control at 9/10 the speed of light. This spaceship is 100 feet in length. And we'll say that it's got a camera, focused on a shipboard clock. Down at ground control, the ground control guy has a TV screen showing the shipboard clock, and he's got his own clock right beside it. So the first question is what is the ground control guy going to see on the shipboard clock? Let's look at the second hand. Let's try this question. How long is it going to take the image of the shipboard clock second hand to go around once, representing the passage of a single minute? 60 seconds, all right? Well, the first thing you do when you're dealing with a relativistic velocity, and this is here's what we need to understand. A relativistic velocity is, generally speaking, any velocity that is 1/10 the speed of light or higher. This is where you're going to see the effects of special relativity. And when you know that you're dealing with a relativistic velocity, the first thing you do is you don't pass go, you don't collect your $200. The first thing you do is you have to calculate gamma for that particular speed. So, gamma is going to equal square root of 1 minus v squared over c squared, which is going to equal square root of 1 minus 0.9c squared over c squared. Now, believe it or don't, you can check this out yourself if you care to. The rules of algebra make it so that I can cancel those c's entirely, and now I can write it this way. 1 minus 0.9 squared, which equals square root of 1 minus 0.81, which equals square root of 0.19, and I got 0.436. That is gamma for any object moving at 9/10 the speed of light. So, here's how we figure out time. Relativistic time is going to equal time is experienced by the moving object divided by gamma. And so in this case, that's going to be 60 seconds divided by 0.436. I got 137.6, which I'm going to round up to 138 seconds. Two minutes. 18 seconds. All right, what does that mean? It means this, that in the time it takes the TV image of the shipboard second hand to go around once, the ground control guy's second hand is going to go around once, twice, and then another 18 seconds there. It's going to take 2 minutes, 18 seconds for that second hand to go around. If the astronaut walks in front of the camera, he's going to appear to be going in slow motion. But here's the weird thing. So far as the astronaut is concerned, he's going to look at his wristwatch and he's going to see the second hand. As far as he's concerned, it's moving at a normal speed. And here's the thing about special relativity. The laws of physics are constant in any frame of reference. So the laws of physics are holding fast for the astronaut, but they're also holding fast for the guy at ground control, but they actually have two different realities going on, and neither one is more valid than the other. What about space? How does space get squished in this? Remember, I talked about space contracting. Well, contracted length, or relativistic length, is equal to original length times gamma. So in this case, that would be 100 feet times 0.436 . 43.6 feet. What does that mean? Well, it means that when this spacecraft goes past NASA ground control, they're not going to see a 100-foot long spaceship. They're going to see a spacecraft that is 43.6 feet long. And it's not an optical illusion. It actually is 43.6 feet long. It actually is. Now, this is a little bit of science fiction, but science fiction is handy because it shows that we can put it into really dramatic effect this way. But where is the evidence for this? Well, some years ago, an experiment was done here in New England. Started on the top of Mount Washington, and if I'm not mistaken, finished up on one of the main beaches. It concerns a subatomic particle called a muon. Okay, atoms are made out of electrons, protons, and neutrons. Protons and neutrons are made out of even smaller particles called quarks. A proton is made out of 2 up quarks and 1 down quark. A neutron is made out of 2 down quarks and 1 up quark. And you've heard of cosmic rays. What are cosmic rays? Well, that's space crap, in a nutshell. It's all the garbage coming in from space. And what happens from time to time, these cosmic rays will hit a bullseye in the nucleus of an atom and bust up a proton or a neutron, and we get these little subatomic particles that are made out of 2 quarks. One type of these particles is called a muon. It's made out of 2 quarks. It has a lifespan of 2.2 times 10 to the negative 6 seconds. Roughly 2 millionths of a second. That's all they live. They live that long, and then they go poof. And when they come screeching down from the upper atmosphere, they come in at a velocity of roughly 0.998 c. In other words, they're within 2/1000ths of the speed of light. So they set up this detector on the top of Mount Washington, kind of a Geiger counter sort of thing, turned it on, it went tick, 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 and yep, we got muons, all right? Now, if you do a little distance equals rate times time, well, this is my time, this is my rate. That comes out, if you multiply these out, that comes out to roughly 600 meters. Mount Washington is roughly 2,000 meters above sea level. So they set up this detector on one of the beaches here in Maine. I think it was Wells Beach, but don't hold me to that. And they set up this detector, turned it on, tick, 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 there's muons. Well, wait a minute, there shouldn't be any muons. They should have all gone piff before they cut down to sea level. How the hell did that happen? Well, if you take into account the effects of relativity, it makes perfect sense. Here's what I mean. Well, first of all, do we have a relativistic velocity? Oh yeah, that's definitely a relativistic velocity. So we're going to calculate gamma for that speed. So gamma equals square root of 1 minus v squared over c squared, which is going to be square root of 1 minus 0.998 c all squared over c squared. We cancel out the c's, and now we get 1 minus 0.998 squared. I got 0.996. Square root of that. Try that again. Let me fix that arithmetic here. Okay. 1 minus 0.996. Yeah, that's better. Which gives me 0.004. .063. Let me just double check that. Okay. So that's gamma for any object moving at 0.998 c. So now, let's take a look at time. Relativistic time, time delta, equals original time divided by gamma, which in this case is 2.2 times 10 to the negative 6 divided by 0.063. So instead of roughly 2 millionths of a second, from our perspective, from the stationary observer's perspective, that muon is lasting 35 millionths of a second. Plenty of time to cover 2,000 meters. Well, what about from the perspective of the muon? Well, remember, one of the rules of special relativity is that the laws of physics are constant in any frame of reference. So within the muon's frame of reference, everything is normal. He's expecting to live 2.2 millionths of a second. And he can make the case that he is a stationary object and that the Earth is coming toward him at 0.998 c. So how does that affect the height of Mount Washington? Well, recall that relativistic length equals original length times gamma, which in this case is going to be 2,000 meters, the approximate height of Mount Washington, times 0.063 From the muon's perspective, Mount Washington is not this, but rather this. And yes, he can cover 126 meters in 2.2 millionths of a second. And this has been experimentally verified. In universities, where we have physics majors, a classic experiment of relativity goes this way. They'll take two precision clocks that will get down to billionths of a second, and they'll synchronize the two. They'll take one of those clocks and install it on a commercial jet, and they'll keep a careful record of how long it traveled, how fast it traveled, and over a course of several months, it'll do the world tour, and then they'll bring it back into the laboratory. And even though the jets were only going in hundreds of miles per hour rather than thousands or millions of miles per hour, it's still motion. When that traveling clock comes back to the laboratory, it is no longer in sync with the stationary clock. It is off by precisely the amount predicted by relativity every time. Every time. And this is why, on a practical level, if you have GPS on your smartphone, that means that you have we're dealing with satellites that are in orbit. The United States Air Force has to reset the clocks on these satellites every month because they are moving at a different rate because of relativity. And if they didn't do that, your GPS would be irretrievably foobarred in about 2 months. So this has been tested and tested and tested. Yes, time slippage really does happen. It's a naturally occurring event in this universe. So now let's have a little fun with this. Let's say that we are going to send a spacecraft out to a star 11 light years away. And we're going to move at 0.998 c. So a round trip will be 22 light years. And just for fun, we're going to throw in this little wrinkle. We have a pair of identical twins. One of the twins is going to go on the journey. He'll be the space twin. And the other twin will stay on Earth, and we will call him, with no small amount of irony, E.T., Earth twin. And they will both celebrate their 21st birthday on the day of the launch. All right. So let's look at it from the perspective of the Earth twin. And we'll rough this one out. 0.998 c, that's just about the speed of light. So from the Earth twins' perspective, traveling at just about the speed of light, it's going to take his brother roughly 11 years to get out to that star and 11 years to come back, 22 light year round trip. So it's for him, it's going to be 22 years before he sees his brother again. He will be 43 years old. All right. Now, relativistic time, that's time as observed by the stationary observer, is equal to time is experienced by the moving object divided by gamma. All right. So that's T delta. Okay? Time is observed by the stationary observer. What about time experienced by the moving object? Well, T is going to equal T gamma times gamma. And we've already calculated gamma for this velocity. Gamma for 0.998c is 0.063. The spacefaring twin will experience only 1.43 years of time. So when he returns to Earth, he will be less than 23 years old. He won't suddenly catch up because he has only experienced 1.43 years of time. Meanwhile, 22 years will have passed on Earth when he comes back. So that's time travel in a very real sense. This is how this universe works. This is how it works. I hope you notice something else too, that the closer we get to the speed of light, the smaller gamma gets. Remember, at 0.9c, gamma was 0.436. At 0.998c, gamma became 0.063. So the closer we get to the speed of light, the smaller gamma becomes. So let's try this one. Let's say that we're going to send a crew out for 1 year of shipboard time. They're going to be going so close to the speed of light that gamma is 0.00001. But they're going to experience 1 year of shipboard time. That means that we're going to put a year's worth of food, water, beer, DVDs, and toilet paper on board that ship to last them 1 year. All right? 1 year of shipboard time. How much time will have passed after 1 year of shipboard time? Well, T is shipboard time. There's gamma. 1 year divided by 0.00001. That comes out to 100,000 years. So if they go out for 1 year of shipboard time traveling at that speed, so close to the speed of light that gamma is 0.00001, when they come back, 100,000 years will have passed, and there's no coming back. It's a one-way trip. Well, let's give them a break. Let's just send them up for 1 day. Okay, so when they come back, 100,000 days will have passed. Well, that comes out to 274 years. "274 years will have passed traveling at that speed for 1 day of shipboard time." The point is, if we're going to get to the stars, it's not going to be a question of muscle. It's not. Because that's a hell of a human toll. It really is. There's going to have to be some other way that we do this. Well, we've established that time and space bend. That we know. Through the Hubble law and through these basic ideas of special relativity, now we know that time and space bends. So we're going to have to work around that problem. But that's for another discussion. But anyway, that's the basic idea of special relativity. Well, one more thing to show you, but that's for another discussion.